Uh, Good morning, everybody. Apologies for the delay with the start of today's tutorial. We were having some Wi-Fi issues, which hopefully we've got sorted out now. So apologies for the delay, and we'll be starting now today's tutorial. Today's tutorial is Algebra 1 and is going to be delivered by Paul Sheehan, who is an electrical engineer. And I'm going to leave it over to you, so Paul, to take from here.
Okay. Thank you, Eamon. Good morning, folks. Paul Sheehan is my name. I've been a volunteer tutor with the CEIA since 2018. Previously, I have delivered tutorials on trigonometry and gone through some exam papers as well with previous batches of students. And this year, I am delivering the Algebra 1 course. Algebra 2 will be next week. I hope in this presentation to build upon the ideas that you've learned last week with Jerry Sweeney and Ed. So without further ado, let's get started. So just by way of a brief biography, describe who I am. My name is Paul Sheehan. I lived in Douglas in Cork. I now live on Watergrass Hill in North Cork. I did the Leaving Cert in 2000, now 20 years ago. And after the Leaving Cert, I did electrical engineering in UCC, and I graduated in 2004. And since then, I've worked in microchip design, that's digital design. And so what I do is I am part of a team that we make chips for mobile phones, and we test them as well. And though I don't use algebra or indeed trigonometry in my day-to-day work, sort of the rigor of problem solving, of breaking down a problem into its constituent parts, and putting it back together again with a proper solution. It's that rigor that I learned in school and in college that I'm applying every day at work. So that is a legacy that I keep from my schooling days. And as I said in the previous slide, I've been with the tutor since for 2 years now. So just by way of just an introduction to what the tutorial is and what the tutorial is not. So this is consistent across the presentations this autumn and winter. So we're not attempting to replace your schooling coursework. We're not a replacement for your teacher, or indeed a sort of a successful interaction, a successful rapport that you have with your teacher. And it's important to build that. And the material that certainly I'm presenting, I'm not pretending that it's exhaustive. It captures all areas of Algebra 1. There are certain gaps that I had to, have simply for time. So it's just important to appreciate that. On a positive note, however, what the tutorial is, this tutorial, like other tutorials that we run, we seek to revisit the fundamentals of the course, just to kind of reaffirm the groundings in Algebra 1, trigonometry, whatever the course may be, because it's essential to have a proper understanding of the underpinning of the mathematics before you proceed with the rest of your Leaving Cert course. We revisit that, kind of re-clarify the rules of thumb, restate rules, and apply them to examples. So hopefully the benefit is that you'll identify, let's say, the problem areas that you may have in your mathematics, and that you sort of take the learning on board and perhaps kind of rededicate your efforts in a particular area of your coursework. Perhaps kind of approach your teacher with sort of a renewed set of questions. Look, I've identified that that this area is problematic. It was raised perhaps in a previous lecture, and I'd like to take this further. So anything that gets you to reassess your comfort with certain aspects of the course, I think, is positive. Above all, the aim of the tutorial as well, and indeed all our tutorials, is to stimulate an interest in mathematics and to kind of put you in the direction of a career in STEM. And mathematics now is the underpinning of many disciplines, be it engineering, science, finance, and so on, particularly the new project maths course. So that is a goal of these tutorials. Finally, nothing in the Leaving Cert Maths course exists in isolation. So, I will make reference to last week's course, just as subsequent tutorials, I hope, will make reference to mine. So, moving onwards. I do think that the sort of a broad appreciation for mathematics draws in sources of information from many different locations. Of course, the Leaving Cert course book and your exam papers are primary sources of information, as is your teacher. But there's so much else out there online as well. Something that I've sort of delved into over the last few years. And I've come across a number of YouTube channels that I think are very interesting. Sort of development of mathematics. They develop ideas, for example. They sort of answer old riddles. They explain kind of cool, key, new areas in mathematics. One of them is Numberphile. What that is, it's a YouTube channel of various postgraduate students in the UK, one of whom is Dr. Hannah Fry. She's a contributor for BBC Radio. And what they do is they explain the science behind sort of card tricks, things like that. They would explain, kind of the mystique of prime numbers and, the way we encounter mathematics in a subtle way in everyday life. I think that's a cool channel, and there are many videos there as well. One thing that they've been doing recently, one of their recent videos, is that they've plotted the growth of, they've described the mathematics behind the modeling of pandemics, such as the coronavirus. And this is one such graph here. So it's all modeled by differential equations. So what they do is they model the number of people who are susceptible to a given disease, those who are infected at a given time, and those who have recovered at that time. And based on, they can toggle different parameters such as the population size, the intensity of the disease, and they can see how over time sort of the pervasiveness of the disease can take effect in a society. And I think the mathematics behind that, above all, are very interesting. Another cool YouTube video as well is 3 Blue 1 Brown. There's a guy, I think he's in the States, Grant Sanderson is his name. He develops in a very almost artistic way problems in geometry, problems in trigonometry, problems in applied maths. The actual graphics he uses are almost as good as the mathematics that he develops. And again, that's a very interesting way to while away 20 minutes. So Mind Your Decisions is one that I've come across most recently. This is a set of questions that are posed by, I think he's a graduate student in Stanford University. And what he does is he receives questions from around the world and he tries them himself, then he presents the solutions. And he gives you an opportunity to do the questions as well. And some of them are very interesting. And some of them are just out of reach of the Leaving Cert course, but by and large, come the end of sixth year, you'll be able to make a stab at most of them. And what's cool about these questions is that they're a synthesis of many different aspects of the course. So there's no one question that's purely on trigonometry, but it's on trigonometry, there's a bit of algebra, there's a bit of geometry as well. It's just kind of a mixture of many different things. So it really gets you to look upon the course as a whole, not just one particular chapter. One very interesting question that I did recently, I'm not going to do it here, but just to give you an idea of the questions that are asked. For example, there was a hollow glass cone, and it was partially full of water. And when the cone is sitting on its base here, the level of the water is 8 centimeters from the top. However, if the cone is inverted and it's standing on the apex, then the level of the water is 2 centimeters from the top. So you have to work out what the overall height of the glass cone is. There's some fascinating mathematics to that. It's not beyond the Leaving Cert course, but it combines a number of different areas of the Leaving Cert course, such as geometry, similar triangles, area and volume, that sort of thing. And it's a nice problem to solve. I did that on the Sunday, the June bank holiday weekend. Anyway, so now the purpose of explaining, of indicating these YouTube videos is just to show you that there is a wealth of information out online, something that didn't exist when I did the Leaving Cert in 2020. It's always good to get a different perspective and just to see how the mathematics that you are learning can be applied to really cool, interesting scenarios. So back to the present. Just by way of an agenda, what I hope to do today is in Algebra 1, I'll give an overview and just of the algebra, particularly the algebra English terms that are used in algebra. We'll go through manipulating equations. Much of this you'll be comfortable with, but it's useful just to go through the basic rules. We'll go through polynomials, they're everywhere. We'll go through factorizing expressions. Then we'll go through simultaneous equations, both with with 2 variables and with 3 variables. And then we'll take a look at quadratic equations and finally cubic equations. Okay, so I mean, algebra, the term dates back to pre-medieval times or even pre-Roman times. It's a term from the Middle East, whereby quantities are manipulated and expressed not in actual numerical values but symbols. And so we deal with unknowns, such as the amount of money in or the amount of whatever, the amount of sheep in a flock or something was denoted by the number X, particularly when it was unknown. And it's manipulating these X and Y values. There are a whole set of rules governing their manipulation such that the integrity of the data is preserved, and that is algebra. And algebra is used throughout mathematics. So whenever I'm working one-on-one with a Leaving Cert student, they might approach me with, I have a problem in area and volume, for example. And irrespective of the area that they'll present, I'll always assess their comfort or discomfort with algebra, because algebra is used throughout the course. There's a reason why it's chapter 1 and chapter 2 in your book. So to have a comfort with algebra sets you up very well for every other part of the course. So algebra in real life, there are many examples online. The best examples that I came across were the examples from Jerry last week. He described a problem where we had to work out Alice's age and Bob's age, and we had to work out as well the optimum perimeter for a Norman window in the side of a church, for example, to assess kind of to maximize the light through that aperture. And I mean, those were pretty good examples of how algebra is used by, for example, architects in the case of the Norman window. Needless to say, if you were manufacturing windows today, it would all be part of a computer program. But ultimately, there has to be a human inputting the algorithms, the algebraic algorithms that are used for that computer program. And it all comes back to a human. It all comes back to algebra and the Leaving Cert. So just to ease us into my own, I have an example here of how algebra is pretty cool. And it's a riddle that I came across many years ago. So take, for example, we have on the left-hand side, we have a theoretical string around the equator of the Earth. And so you can imagine that the equator of the Earth is kind of a string or a belt going around it. And so someone cuts the string and splices in a new 1 meter section. So now the string is not quite as snug around the equator of the Earth. If you were to distribute it uniformly, there's a gap all the way around the Earth. So the question is, what is the width of that gap, right? You're thinking that, well, given the size of the Earth and the relatively small 1 meter section you put in, it's probably minuscule. Okay, well, let's check that through algebra. So let's put down some numbers, or not numbers, but but symbols to represent our problem. R is the radius of the Earth, and X is the gap. So X will generally be an unknown. Okay, I choose the values R and X for obvious reasons. So what we do then is we express in an algebraic equation, we convert our English scenario into the algebra that represents it. So on the left-hand side of this equation, we have 2 pi r plus 1. So 2 pi r is the circumference of the original string, and we add 1 to it because that's the meter section that we put in. And what does that equal to? Well, the 2 pi r plus 1, that string, the string of that length, it is now the circumference of a slightly larger circle than before, the circle being a circle of radius x plus r, okay? The original r plus the x. So that is, the circumference of that circle is 2 pi into r plus x. So that is our equation. So what we do then is we solve for x, okay? So we multiply it out, 2 pi r plus 1 equals 2 pi r plus 2 pi x. Okay, and we can remove 2 pi r from both sides. We have 1 equals 2 pi by x, x equals 1 over 2 pi, x equals 16 centimeters. Okay, the algebra is used to work out this problem, and I think it's a cool solution. I first found this when I was 7 or 8, having done the area of a circle and so on, and circumference in school. When you add in the meter into this string, the gap around the Earth is 16 centimeters, which I think is a fascinating solution. You would think that given the Earth is so huge and the meter is so short, that the gap would be minuscule, but no, it's pretty significant. It's 16 centimeters. And all that is done by algebra. We didn't have to know the area of the Earth. We didn't have to involve the value of pi. So I think just that's a nice sort of it's regarded as a riddle online. Not really a riddle. It's an algebra problem, and I just think it's an interesting application of algebra. Right. In your algebra course, you have encountered a lot of English terms that are used very much in an algebraic sense, and it's important that we go over them because they're often used interchangeably. They're often mistakenly used interchangeably, and I think it's important just to nail them down. So we have I'm sure you've heard the terms: term, coefficient, expression, and inequality. Now, inequality will be done in the Algebra 2 part of the course. I don't do inequalities here. So, an algebraic expression is a string of many terms, okay? And a term is sort of a fundamental constituent of an expression. And a term can be, and the consecutive terms then are bound together by operators such as a plus sign, a minus sign, a division, or a multiplication, for example. So just by way of a simple example, this is an algebraic expression here. It's algebraic because we're using the x to represent unknowns. We're using y to represent another unknown, for example. And each thing here in this expression is a term. So the 2x squared is a term, the 3x squared is a term, the 4x squared is a term. They're all terms. And another English word you might use in everyday life is the coefficient, okay? And the coefficient is the number that goes with the unknown. So for example, the coefficient of the xy term is 3, the coefficient of the x term is 4. So coefficient, the thing that goes with. And again, you'll hear that term mentioned at speed in your class, but that's what it is. It's just the number standing next to the unknown, okay? Now a constant is, in this particular case, is 7. A constant is something that never changes. So the 7 will always be 7. 7 was 7 yesterday, 7 will be 7 next week. However, 4x is not a constant. It can change depending on what x is. when x changes, 4 changes. So sorry, when x changes, the 4x changes. So it's not regarded as a constant. Okay. And another thing to draw from this algebraic expression as well is the notion of like terms. So terms that are like the apples and apples, the ones that can be manipulated together. Okay. So 2x squared and 3x squared are like terms because they can be combined. Okay, they make sense with each other. So 2x squared plus 3x squared is 5x squared. 3x squared minus 2x squared minus 3x squared be minus x squared. However, the 2x squared and the 3xy are unlike terms, meaning that we can't simplify that any further. 2x squared and 3xy, I mean, what would their result be if you added them? What would their result be if you subtracted them? So they're unlike terms, okay? And expressions, as I say, are made up of terms. We have here, kind of a subdivision of expressions. We have a monomial expression, that's just one term. A binomial expression, that's 2 terms. A trinomial expression, that's 3 terms, and we could go on. You probably won't hear the terms monomial or trinomial very often. You will hear binomial. And to generalize it then, a polynomial is an expression with many, many terms. Basically more than one. Poly coming from the Latin, meaning many. Okay. Sorry. So another English term that you'll hear in algebra is equality. An equality is basically an algebraic statement with an equal sign in the middle of it. So it has two sides, a left-hand side and a right-hand side, and both sides are equal to each other. Okay. And an equation is an equality but it is true for some, but not necessarily all of the variables in the equality. So for an example, the first equality here is x squared minus x minus 6 equals 0. So that's true for some values of x, but it's not true for other values of x, okay? Sine of 2x equals 1/2. Again, it's true for some values of x, but not for all values of x. And when I mean that, like, every equation has a solution set, and very often the job in Algebra 1 is to find these solutions. The job in algebra is to find these solutions. What is the solution set? And an identity, this is another thing that crops up reasonably often in algebra. So an identity is an equality statement, but in this particular case, it's true for all values of the variable. And irrespective of what value you choose for the unknown, be that x or y, the left-hand side will always equal the right-hand side. So we have here x squared minus x minus 6 equals x minus 3 by x plus 2. So no matter what value of x you choose, the left-hand side will equal the right-hand side. And so you could say that it's a bit of a tautology insofar as the left-hand side is merely another way of writing the right-hand side. 6 of one, half dozen of the other. It's almost that analogy. And that's why they're called identities. Another one is x squared plus 2xy plus y squared. That is the same as writing x plus y all to be squared. Okay. A formula is like a recipe, a way of doing something, a method that gives you the result. And that in mathematics, a formula will generally have variables or unknowns that can be combined together to give a result for a specific situation. So the formula, a volume of a sphere, for example, 4/3 pi r cubed. But if I presented that to you, but it was outside the context of a sphere, it would be pretty much meaningless. Okay, a formula always has to be presented, but in the context of something. Now, working with equalities is is a key thing in algebra. One must preserve the equality at all times. So whatever you do to the left-hand side of an equality, you must do it to the right-hand side in order to preserve it, else it's no longer an equality. And that involves sort of transferring values from one side of the equality to the other. There are rules governing that operation, and those are all the rules of algebra. So, as I say, what we do to one side, we must do to the other, otherwise it's no longer an equality. So take, for example, this very trivial example here. Minus y equals 3x minus 2. You might recognize that as a linear equation in coordinate geometry. We decide to multiply both sides by minus 1 because it's normal to keep, in this particular, in coordinate geometry, it's normal to keep the y positive when it's expressed like this. So we multiply across by minus 1. We have to do it to the left-hand side, and we have to do it to every term on the right-hand side, okay? When we're removing a term from one side to the other, we reverse its operation. So take, for example, this one here. It's 1/3 by y plus 1 equals 2x. So the 3 is a dividing term on the left-hand side, but it becomes a multiplying term on the right-hand side. So what we're doing basically is we're multiplying both sides by 3. So in a colloquial sense, you bring your 3 up from the left-hand side to the right-hand side. Just want to do another similar example here. This is the first time I'm using the whiteboard. Let me know if you have any issues with this. Can you see the whiteboard there? Let me know if you can. So say, for example, we had a case whereby we had an expression, sorry. So let's say we had 1/5 by x minus 2/3, and that was equal to 7y plus 2. Okay, now let's say we wanted to isolate x. Okay, so isolate Okay, so what we cannot do is we can't do something like this. We cannot do, and you know what I'm going to do? I'm going to write it in red. Okay. So we cannot say x minus 2/3 equals 5 times 7y plus 2. Okay, we can't do that because it's not as if the entire left-hand side was multiplied by 5, okay? Only one particular term on the left-hand side was multiplied by 5. So what we must do in order to isolate x, we could say let's write the start back down here. Okay, we say 1/5 by x equals 7y plus 2 plus 2/3, and then we can multiply across by 5. Plus 2/3. Okay, so a trivial example. I'm sure many of you would not make this mistake, but it's just important to be aware of these little rules in the heat of an exam, because that's when the mistakes can. It is in that environment that the mistakes can leak in. Okay. So that was just a first foray into the whiteboard. Let me know if there's a problem. Now, I go back to the.
Sorry, Paul.
Yes.
We can't see the whiteboard at all.
Oh gosh. Okay. I'll just restate what I was doing. Okay. Can you see the whiteboard now?
Yes, I can see it.
Okay, so let's say I had, sorry, I just skip through that again. Let's say I had 1 over 5 by x minus 2 over 3, okay, equals 7y plus 2, right? I can't do the following. I can't say x minus 2 over 3 equals 5 times 7y plus 2, okay? Because the entire left-hand side was not multiplied by the 5. Was not divided by the 5. Only one particular term on it was. So this is wrong, okay? What one must do is, in order to isolate the x, one must say, well, 1 over 5 times x equals 7y plus 2 plus 2 over 3, and then we can multiply up by the 5, okay? It's plus 2 over 3, okay? So it's a fairly trivial example, but as I said in the previous case, you know, issues like that could creep in the heat of an exam. So it's important to just be mindful of the rules, be mindful that you're preserving the equality of an equation, okay? Again, very trivial, and I'm sure none of you would make that mistake. So I'll go back to the PowerPoint presentation. Okay, can you see the PowerPoint presentation? So another thing in algebra, again, governing the transfer of variables from one side of the equality to the other, is changing the subject of the formula. So this is the area of a circle, a equals pi r squared. So here a is said to be expressed in terms of r. So if we know r, we can work out a, all right? But let's say, for example, if you didn't know r, you knew a instead. Well, you can rearrange it as, if you wanted to isolate or, for example, you bring your pi, you divide both sides by pi, and then get the square root of both sides. And that's what we have here, or equals the square root of a divided by pi. So now if we know a, we can find or. And just as an aside, I see that repeatedly throughout questions on the Leaving Cert. You know, you know one thing, but you often have to use the formula in the reverse way that was originally intended, something like that. So you have to rearrange the formula into its kind of less familiar expression. Like this would be a less familiar way of expressing the formula for the area of a circle. So it's this sort of comfort that's required with manipulating algebraic expressions is very important. It crops up time and time again, not just in the algebra part of the course, but in every other part of the course. Just an exercise here. I'll give you just a moment, perhaps maybe 3 minutes. Can you transcribe that particular formula? I believe it's a formula used for in physics. Can you take down that formula, please, and just express k in terms of the other variables? So express k in terms of t, g, and h. Okay. So I'll just give a minute on that, just to get you thinking. So again, this, as I say, it just governs, it just checks that you're familiar with the laws that govern the manipulation of algebraic formulae, algebraic expressions. So I'll just get that ready on the whiteboard. So it was, t equals 2 pi by the square root of h squared plus k all over 2gh, right? So express k in terms of tg and h, in terms of now. I wouldn't normally write down the question in an exam scenario, but I'm just doing it here for clarity. So we want to isolate. So again, we want to isolate k. In other words, get k on one side and everything else over to the other side. So the first way to isolate k, we have to get out of under that square root sign. So we start to isolate it. We say t over 2 pi equals the square root of h squared plus k all over 2gh. Okay, and then what we'll do to get rid of the square root, we'll square both sides. Again, as per the rules, we're doing the same thing to each side. Okay, and that is h squared plus k all over 2gh, right? And now if I bring that up here, okay, we have t squared all over 4 pi squared, and that equals h squared plus k all over 2gh. And then we have t squared by 2gh all over 4 pi squared minus or equals h squared plus k. Okay, so our last step is k equals t squared by 2gh all over 4 pi squared minus h squared. So needless to say, it's not as elegant as the original expression, but nevertheless, it is k expressed in terms of the other variables. So I'm not particularly sure what this scenario is, but if you knew t, g, and h, then you can work out k. Okay, and notice at each stage, I just obey the laws of the algebra. Whatever I did to one side, I did to the other, and if something was subtracting on one side, well, then it was added to the other side. If something was divided on one side, it was multiplied on the other side. And a further simplification I can make here, I can divide above and below by 2 just to express it in its simplest form. Okay. Okay, so I'll go. Thank you for that. I'll go back to the PowerPoint presentation now. So that is the final expression there. Okay. So another way of manipulating algebraic expressions is to, and I sort of hinted it in that example, is to square each side as a single unit, square the left-hand side and square the right-hand side. So by way of an example, so we have x equals a plus b. So therefore we can say that x by x equals a plus b all by a plus b. And the reason why we can multiply this side by x and this side by a plus b is because x and a plus b are the same. So we're multiplying both sides by the same thing. Okay, that's why this is a legal operation. So then we can say, well, just tidy it up, x squared equals a plus b all to be squared. Okay, a possible pitfall to fall into here is if you were given x equals a plus b to square every single term. That's incorrect. Okay, we have to square the left-hand side and we have to square the right-hand side. we're not doing that in this particular scenario. That was actually pointed out again in one of the first, I sat in on one of the first CEIA tutorials a few years ago, and I think it's just a very relevant thing to do. It can be done easily. This mistake can be done easily in the, as I say, in the heat of an exam, and it's just important to be very wary of that. Okay. So the next, just a caveat on squaring both sides. Oftentimes we have to check the solution of these problems that involve squaring both sides. So say, for example, we had a equals b. We can square that equal to square both sides. We have a squared equals b squared. However, also a equals minus b, we square both sides and we come out as with the same thing, a squared equals b squared. And when we solve this particular solution, a squared equals b squared, the solution that we get could be for either a equals b or a equals minus b. So we must check the result of what we're doing. Okay. Oftentimes we might have to discard a solution. Okay. Just to extend that a little further, we can raise, not only square things, but cube at both sides of an equality. So we have x equals a plus b, then x cubed equals a plus b all to be cubed, x to the power of n equals a plus b to the power of n. Okay. So I just want to go through a Leaving Cert paper with that in mind, how to solve the equation x equals the root of x plus 6, and x is an element of OR. Okay, so the question that I have at the moment, before I do this solution, do you know what OR means? Okay, and Ed has a poll on that right now. Okay. Okay, very good. Encouraging answers there, thank you. So Jerry would have touched upon this, the notion of OR numbers last week, whereby OR means real. So they're any number that can be represented on a finite or infinite decimal expansion, and they're the superset of natural numbers, integers, rational, irrational numbers, and they're distinct from imaginary numbers. So it's oftentimes, I've noticed before with a few students of mine that, you know, this little piece of information that's added to questions can often seem quite odd, a little bit off-putting. But basically what he's telling you is that the x has to be a real number. So he's kind of telling you, he's giving you an idea of what your answer will be. And if your answer you get for x is not a real number, well then you know you've gone wrong somewhere. So often just try and extract as much information from the question as possible. And recall Jerry's Venn diagram of the different types of numbers last week. Okay, so let's do that particular question in the whiteboard. And share the other one. So we have x equals the square root of x plus 6. So what we do is we square both sides. So that's x by x equals the square root of x plus 6 by the square root of x plus 6. Okay, that's x squared equals x plus 6. Okay, and get everything over to the one side. Okay, and we can factorize this. This is a quadratic, and we'll come up against quadratics later on in the presentation. And we can factorize that as x plus 2 and x minus 3. Okay, so therefore x equals -2 or x equals 3. So if two things multiply together it gives 0, one of them must be 0. So what we do is we check their solutions just to make sure everything's okay. So we check x equals -2. So we sub into the original expression. So -2 equals the square root of -2 plus 6. -2 equals the square root of 4. And that's not true because we're going for positive roots of numbers. The second one, check x equals 3. Well, then 3 equals the square root of 3 plus 6, and that's true. All right. As I say, the square root of 4 is understood to be the positive root of 4. So if I go back to the PowerPoint presentation again. Another algebraic manipulation that you might have to make is taking logs of both sides of an equation. And Ed reviewed this particular area last week. So if we had an equation x equals y, then we can say that log of x to base a equals log of y to base a. Or if log of x to base a was equal to log of y to base a, well then x equals y. Okay, and just a caveat here, if a is greater than 0, then log of x to base a is defined only when x is greater than 0, right? So there might be times when you might have to take logs of an equation. That's probably in the later algebra section of your course. You might have to take the natural log, for example. Just another example, just to use that theory, we're given that a to the power of 3x plus 1 equals 5b minus 2, and we have to write x in terms of a and b. So we have x, we want to have x on the left-hand side of the equal sign and a and b on the right-hand side of the equal sign. And then there's another question, if a is greater than 0, for what values of b is this formula valid? Okay, so we have a to the power of 3x plus 1 equals 5b minus 2. So we want to get rid of the indices, okay? And the indices, as Ed said, is the power. Well, we take the log of a to both sides. Therefore, the log of a to 3x, the log of a to the power of 3x plus 1 to base a, that equals the log of 5b minus 2 to base a, okay? Using your rules of logs, you can bring down your power to the front. So therefore, 3x plus 1 by log of a to base a equals log of 5b minus 2 to base a. Then we know that log of a to base a, by what power must you raise a to get a? Well, that's 1. So therefore, that's 3x plus 1 equals log of 5b minus 2 to base a. Rearrange using algebra. What I'm doing is I'm bringing my plus 1 over to the right hand side, making it minus 1, and I'm dividing both sides by 3 in order to isolate x. And then we have x equals 1/3 by log of 5b minus 2 to base a minus 1. And another thing here is when your sort of expressions start to expand in algebra, just watch for your brackets, okay? I often used a mixture of, sort of curved brackets and square brackets and braces, and it doesn't matter how much paper you're using, right? Just make it nice and clear for yourself and for the examiner. I mean, this is a relatively small expression, but they can increase in size. So the latter part of the question was, for what ranges of A is this, for what range of B is this solution valid? I mean, the log, the number of the log has to be greater than 0. So 5b minus 2 has to be greater than 0. Therefore, b has to be greater than 5 over 2. Okay. So we've done a number of the rules now in algebra, how to manipulate an algebraic formula, how to apply roots, how to deal with square roots, how to deal with squares, how to deal with logs, relating like terms with each other, for example, managing indices in your algebraic expression. Polynomials. So polynomials is we touched on the term before. It has many terms, anything more than 2. Okay, and the definition of polynomial is that it consists of variables and coefficients and constants, and they involve the regular operations of addition, subtraction, multiplication. But interestingly, with polynomials, is that you must have a non-negative integer indices or exponents, powers must be used, okay? And we'll come across a few examples in a second. But what is just a real-life example of a polynomial? We have a plane here, and it's coming into land at an airport. And if you've ever done so, you'll notice that the plane descends on sometimes a very shallow arc, and which can extend over many miles. And the plane has a pre-programmed trajectory that it must follow going into the airport. So at various distances, horizontal distances to the airport, it must be at a certain altitude at each of those points. So the profile or the curve of that trajectory can be described by a polynomial in x, or in this particular case in L and x. So the computer will know at a given point, at a given horizontal distance from the airport, what altitude it must be at. And then if it's not at that altitude, to make the correction as appropriate. Now, I say polynomials in real life. Admittedly, this is with respect to airline pilots and aeronautical engineers only, perhaps, but it just shows how trajectories, the paths that a plane must take, the path that a robot has to take, for example, on a factory floor, they are defined by polynomials. They're pre-programmed as polynomials. Okay. Oftentimes, the unknown, the x, being the distance from an endpoint or the distance from the start point, for example. So that's a polynomial here in airline flight. And polynomials come in different forms, all depending on what the highest power used in the polynomial is. So 4x minus 6, that's a polynomial with degree 1, because the highest power is 1. And we have a quadratic polynomial, the highest degree is 2, so it's of degree 2. And finally, we have of degree 3, okay? And I've highlighted each of the degrees here. It's the highest power. I remember that the first year in engineering and mathematics in college, they went into polynomials in a big way, and they were always referring to the polynomial by whatever the highest power was, irrespective of how many terms were in that polynomial. They would call this a degree 4 polynomial, a degree 5 polynomial. And the degree that was used would give an indication of the underlying graph, that would result if you actually drew it. So as soon as we saw the polynomial, we had to get a sense of what was the underlying trajectory, what was the underlying curve of this polynomial. And it was the degree that betrayed what that curve was. So that's why polynomials are referred to almost first and foremost by their degree more than anything else. Okay, we want to know the shape. And ultimately, that's what a polynomial is. It's not merely a string of algebraic characters, it does represent something in the physical world, as I say, be that the trajectory of a plane or the path of a robot on the factory floor, for example, or maybe if a robot was painting the side of a car, for example, you could imagine the very tip of the robot describing an arc in space. Okay, well, they would want to know how would you describe that arc with the polynomial, such that, I don't know, that it wouldn't hit the car or something, or that it would apply the paint in as smooth a manner as possible. Okay. So there's another poll question here. Can you identify which of these 4 expressions is a polynomial? So only one of these is a polynomial. Okay, I'll just hold off until the results are in. Okay, cool. Okay, most people said C. Correct, that is the one that's a polynomial, because I'll just go to the next slide. Because if you recall, the definition of a polynomial was non-negative integer exponents have to be used, non-negative integer exponents. So this 1 over x is the same as x to the power of -1, so that's a -1. This has x, the root of x, so it's x to the power of 1/2, and this is x to the power of 3 over 2, okay? This is the only one which has non-negative integer exponents used. That's a 3 and that's a 1, okay? We won't come across that distinction too often you won't come across that distinction too often in your course, but it's just a good idea just to understand what the real definition of a polynomial is, okay? So polynomials can be added and subtracted. So we have 2 polynomials here, x cubed minus 2x squared minus 5x minus 2 plus 3x plus 4x squared minus 3x cubed. And what we do is we multiply in by the -1 here, okay? And just watch your signs. And then what I do here is I identify the like terms, the terms that will go together, and more importantly, perhaps the terms that will not go together. So we have an x cubed here, and we have an x cubed out here. So I'd label them the same. We have a 2x squared here and a 4x squared here. I'd label them the same. We have a 5x and a 3x, and we have a constant then. So I'm not suggesting perhaps that you do this in your solutions. There's no question of labeling, but just in your mind to say, oh yeah, this term will go with this term will go with this term. If you want to, then rewrite it perhaps with the terms grouped together. That can sometimes help, as I have done here. And then, only then, do I apply the actual arithmetic operations that are in the pluses and the minuses. So we have 3x cubed minus 6x squared minus 8x minus 2, okay? Then multiplying polynomials, every term in the first polynomial is multiplied by every term in the second polynomial. And then, if necessary, we can simplify with addition or subtraction. Recalling Ed's presentation from last week with indices, when we're multiplying 2 terms like the x and the 2x squared, we add the indices. So we multiply this out. I rewrite it explicitly here, x by every term in the second polynomial minus 5 by every term in the second polynomial. And then that's 2x cubed minus 3x squared plus 6x minus 10x squared plus 15x minus 30. I tidied up, bundled together my like terms, and be mindful of the unlike terms. And I have 2x cubed minus 13x squared plus 21x minus 30. Now, dividing polynomials, I've deliberately left this till later, but Oftentimes you can factorize, you can simplify a polynomial into its constituent parts and maybe do some cancellations above and below the line, or else you can do long division, and we'll come up against the long division shortly, okay? So another way that polynomials are used is that they can be used to represent, well, one way that they're used is they can be used to represent functions. So a function, as you know from elsewhere in the course, applies a rule to a certain variable to produce a result, and the result will depend on both the function and the variable used. And the function can be expressed in terms of a polynomial. So for example here, if we had the sides of a rectangle were expressed as 2x plus 3 and x plus 2, you could say the area of the rectangle is 2x plus 3 multiplied by x plus 2, and multiply that out, and so the area as a function of x, in other words, if our x value changes then the overall a will change. You could say that the area as a function of x is 2x squared plus 7x plus 6. So if the sides of the rectangle had this relationship with each other, well then the overall area would be found by this, okay? It's just a simple example of how a function can be represented in terms of a polynomial. And I've come across other functions, for example, some of them are a bit outside my scope. For example, they might have, you know, in finance, the depreciation of a certain asset, for example, you know, is a function of the original value of that asset, and you could like the depreciation curve can be described by a polynomial. There are examples of that online. As finance, as kind of all that area gets ever more mathematical, so they are borrowing principles from algebra. So another very important part of algebra is factorizing expressions. So that is finding the factors of individual expressions. So factors are those things that when multiplied together give back the original expression, okay? I was going to put in a 10-minute break here. Do you mind if I maybe drop it down to 5 minutes, because time is clipping along and I still have more to do? Is that okay, Eamon?
Hello, Paul. Yes, that's fine.
Okay.
So for students, so if we could be back here at it's now 11:14, say 11:20. If we could be back here to start at 11:20.
Very good. Thank you.
Okay. Thanks, Paul. Thanks for
that. One way of factorizing expressions is to, again, factorizing means to find what are the 2 or 3 or 4 things that will multiply together give you back the original expression. And the example here that I have is 3x squared minus 9xy. So you could take out the highest common factor of each, which is 3x. So that's 3x into x minus 3y. Okay. Another way of factorizing expressions is to watch out for similar expressions. Okay, watch out for similar terms. So we have 6x squared plus 2a minus 3ax minus 4x, and we could rearrange this as the 6x squared minus 3ax plus 2a minus 4x, and take out the highest common factor of the first two terms, which is 3x, such that we have 3x into 2x minus a, and then how can this same 2x minus a be used to generate the last two terms? Well, the last two terms can be generated if we use minus 2, okay? So minus 2 by the 2x minus a. So therefore we have, if we can take the 3x, the minus 2, multiplied by the 2x minus a. And to prove it then, what you could do is, to be pedantic, you could multiply this out to get back this original expression, okay? So the key here is just to see what terms are sort of similar to each other, and how you can pair them off like this, okay? Another way of factorizing expressions is look for common patterns, and they do arise repeatedly in the leading cert. So we have the old favorite, this difference of two squares, which is the first minus the second by the first plus the second. And sometimes it's disguised. So we have x to the power of 4 minus y to the power of 4. Well, that is x squared all to be squared minus y squared all to be squared. Okay, so then we can factorize that using the exact same rule as before, and we can factorize still further. It's always good to factorize to its simplest form. In other words, it can't be factorized anymore. So, and I say these are sometimes disguised, and yes, they are disguised. So he might use sort of the common perfect squares like 4, 16, 60, 64, for example. Those numbers occur repeatedly. And similar to that, how can we factorize the difference of the sum of two cubes? And again, there are rules for those which you just have to learn off. And again, some questions will disguise cubes. So you'll have, you'll have 27, 81, 125, for example. They're all cubes of numbers. And it's just important to know for each of the numbers, let's say 1 to 12, what are their corresponding squares and what are their corresponding cubes, because those numbers will appear. They do appear all the time. So I have another example here of simplifying algebraic expressions, okay? And I'll go back to the whiteboard. So we have to simplify. Sorry. We have to simplify 3 over x minus 2 over x plus 1. X minus 1 minus 4 over x by x minus 1. So like fractions, you can only add and subtract fractions when they have the same denominators. So what we do is we get everything to have the same denominator. So we can say 3 over x by x minus 1, but we have to multiply that by x minus 1, because the x minus 1 will cancel with the x minus 1. So we're back to the x over 3. So we haven't really done anything as such. Okay, and then we have 2 over x minus 1 by x, and we have to multiply this by x to preserve the original fraction, and then we have 4 all over the x minus 1. Now, because they all have the same denominator, then we can add them. Okay, so the rules for arithmetic apply for the rules of algebraic manipulation as well. So then multiplying the 3 by the x minus 1, we have 3x minus 3 minus 2x minus 4, and that tumbles out to be x minus 7 all over x by x minus 1. Okay, and oftentimes these questions sort of simplify this fractional algebraic expression. They'll come up in part A of a question, and the subsequent questions might use that result, sometimes not. But that's when they generally occur. That's when I've noticed them. Okay, so if I go back to the PowerPoint presentation, so we're into the area now where we mix algebra with coordinate geometry. So we have a linear equation with two variables, and this particular equation is 2x minus 5y equals 9. So that can be represented on the xy Cartesian plane. So the reason why this particular line is labeled 2x minus 5y equals 9 is because for every single point, for example, every single point on this line has an x and y coordinate, okay? This particular coordinate here is x1, y1. And when you plug the values x1, y1 into this formula, you will get 9. The formula agrees, the formula works, okay? Similarly, when you plug x2 and y2, whatever those values are, I don't know, but they satisfy this formula. So this expression, the 2x minus 5y equals 9, it is met by every single point on this line. And that's why so this line is merely a collection of all those points that satisfy this expression. Okay, the point out here, for example, whatever that coordinate is up here, if you were to sub that into the line, it won't, the x and y value, if you were to sub them in, it won't equal 9. So that's why that line, that point, is not on the line. Okay, that's just the relationship between the linear equation and the actual graph of that line. That's the relationship between the two. Similarly, this is another line. This is 3x plus 2y equals 4. And for every point on this line, the x and y coordinates for those points match or satisfy this expression. Okay. The question then is, what happens if we have two such linear equations? We have the blue line here and the green line, and we want to find out where they intersect. Okay, so we want to find out the x and y pair that satisfy both of those lines at the same time. In other words, simultaneously. Okay. So what I'm going to do, I'll just quickly run through that on the whiteboard. There's this is just a standard way of doing that problem. So if I do, sorry. I do, one moment. So I write out the formula here. So it's 2x minus 5y equals 9. And it's always good to label them with a capital letter. Okay, so it's a and b. So 3x plus 2y equals 4. Right. It's what we want to do is we want to eliminate one of the variables. We have two variables. We have to eliminate one of them. Okay. So what you can do is you multiply a and b such that the coefficients, these numbers here, the coefficients of one of the variables, either x or y, are the same. So what we're going to do is we're going to multiply a by 3. Okay. So therefore we have, sorry, that's that equal sign shouldn't be there. So we have 6x minus 15y equals 27. And we're going to multiply b by 2. Okay, so therefore we have 6x plus 4y equals 8. Okay, so then what we do is we subtract one of the linear equations from the other. So 6x minus 6x, it's gone. Minus 15y minus plus 4y, that's minus 15 minus 4 is minus 19y, and 27 minus 8 is 19. Okay, so therefore y equals minus 1. Sub the minus 1 back into either one of the original expressions. Okay, I'm going to sub it back into a, and therefore we have 2x plus 5 equals 9. Therefore 2x equals 4 because we're subtracting 5 from both sides, and we have x equals 2. So the point at which they intersect is 2 minus 1, okay? 2 minus 1. If you were to sub in 2 and minus 1 into a, you would get, that would satisfy. And if you were to sub in 2 and minus 1 into b, that would satisfy as well. So we found the line, we found the point that satisfies both equations at the same time, i.e. simultaneously. Okay. So I'll go back to the PowerPoint presentation. Then we have a solution with linear equations with 3 variables. So this just extends the x and y plane in the z direction in the 3 dimensions. So we have, just by way of, just to describe it, we have a point here called 3, 4, 5. It's 3 in the x direction, 4 in the y direction, and 5 in the up direction, the z direction. Okay. So in the 3D space, the linear equation with three variables, x, y, and z, represents not a line, but a flat shape, a plane, okay? So this is a linear equation with 3 variables here. That's the first one. This is another linear equation. And then this is a third linear equation. And what we want to do now is, like, just imagine 3 sheets of paper all sort of existing in the three-dimensional space. They'll all meet at a certain point. Okay, so the question is what that point is. What are the values of x, y, and z that satisfy each of those 3 equations? And that point is somewhere here. The graphing tool isn't great, okay? But the method for that is largely the same. So I'll go to my whiteboard and I'll clear all drawings. So when we have 2x plus 8y minus 3z equals minus 1, we have 2x minus 3y plus 2z equals 2. We have 2x plus y plus z equals 5. We'll call that A, we'll call that B, we'll call that C, okay? So what we have to do, we have 3 variables. We have to remove one of the variables and go back to the old case of two simultaneous equations in terms of 2 variables, and then reduce it down gradually to find 1 variable, and then sub back. So in terms of the practice, let's say we take A and B, okay? So A is 2x plus 8y minus 3z equals minus 1, and B is 2x minus 3y plus 2z equals 2. Okay, again, as before, subtract 1 variable from the other. So 2x minus 2x is gone. 8y minus 3y is 11y. And minus 3z minus 2z is minus 5z. And minus 1 minus 2 is minus 3. Now, since we've committed ourselves to removing x, we have to take the other two equations and remove x from them as well. So we have b, we have 2x minus 3y plus 2z equals 2, and we have 2x plus y plus z equals 5. And again, subtract one expression from the other. So 2x minus 2x cancels. Minus 3y minus y is minus 4y. And 2z minus z is z. And 2 minus 5 equals minus 3. So we have 2 new equations here. We eliminated the x, and we have 2 new equations in y and z. We'll call this D, and we'll call this E. Okay? What we do then, we're back then to our previous example whereby we have 2 equations and 2 unknowns. And again, we have to eliminate something else. So now what we do is we let's say we multiply, let's say we try and eliminate the z's, okay? So we take d and we say 11y minus 5z equals minus 3. And let's say we multiply e multiplied by minus 5, okay? So that's minus 4 by minus 5 is 20y, and z by minus 5 is minus 5z, and minus 3 by minus 5 is 15, okay? So then 11y minus 20y is 9y, is minus 9y, minus 5z minus 5z, so it's minus 5z plus 5z, which is 0, and then, so they cancel, so it's minus 3 minus 15, that's minus 18, so y equals 2. All right, so you see the way how we've gone from 3 equations and 3 unknowns to 2 equations and 2 unknowns, and then we find the value for z, okay? The reason why so I looked at D and E, okay, and I wanted to make my life easy. I wanted to see which of the 2 variables, y and z, I could remove. And I thought it was easier to remove the z's. All I had to do was multiply the e by, minus 5, such that they were the same. It would have been more difficult and more arithmetically tedious to make the 11 match the 4. Okay, what's the lowest common multiple? What's the lowest common multiple of 4 and 11? That's 44. That gets a bit chaotic. Okay, so I went for the z's. Okay, so I found that y equals 2. So I sub y back into either of these expressions, and if I do that, I'll find that z equals 5. Okay. So now I have y equals 2 and z equals 5. I have to find x. So I sub them back into any one of these expressions here, the original expressions, and I find that x equals minus 1. Okay? So the point in the 3D space where 3 planes coincide is minus 1, 2, and 5. Okay. Now it's very easy. It's very easy to make a mistake here in an exam, manipulating signs or just doing some sort of arithmetic mistake. So it's important just to watch out for that, because, and just be mindful of the theory, but also be mindful as well of the of just the scope for making a little slip up. Okay. I'll just go back to the PowerPoint presentation. Right, so quadratic polynomials, the quadratic functions. So this is the bread and butter really of the Leaving Cert course. So this is a 2-order polynomial, and it's a polynomial in degree 2. This example here is x squared minus x minus 2. So that can be represented as a graph on the Cartesian plane. So just like the linear equation earlier on, every point on, if you were to sub in the x and y value of every point on this curve, it would match this particular expression. It would match it, okay? That's basically what it is. The line just joins up all those points which meet that expression, okay? Now, the big thing about quadratic expressions is to find where f of x equals 0. So to find where, so f of x is some function of x. So for every x value, we put it into the function, and the output is f of x. We have put a function on x. But we want to know is where f of x equals 0. In other words, where it crosses the x-axis, okay? They are known as roots, okay? And that's basically what I've described here. In this particular example, f of x equals x squared minus x minus 2, the roots, or where it crosses the x-axis, are x equals minus 1 and x equals 2. So if you were to sub minus 1 into this particular expression here, y would be 0, or f of x would be 0. If you were to sub 2 into this expression, the output would be 0 as well, okay? So there are a number of different ways of finding the roots of a quadratic expression, and you know, you can do it by inspection. Probably at this stage at the Leaving Cert, if you had 3x squared minus 13x minus 10 equals 0, well, you can factorize them like this. Now this is a kind of a simple example because 3 is a prime number, so you know it's 3 by 1. But what you do then is you factorize the constant out here, such that when it's multiplied by the 3, it'll, you know, and this other term is multiplied by the x, it'll give you the middle term here, okay? So there are various rules for doing that. I won't go into them in detail here. I encourage you to look at the rules of thumb in your book. But the more practice you get by looking at an expression like this and sort of seeing what the potential pairs of values are, there's a big skill in that, okay? That's kind of a good skill to have, you know, and you'll find with enough practice that the actual values will jump out at you, and that's a good place to be at. However, if it doesn't come, there is a get out of jail free card, as you know. So just to continue this example here, we factorize this quadratic, and if both of them are multiplied together give you 0, then one of them must be 0. So we equate each of the factors to 0, and we find what these values of x are. Okay, that should be x equals minus 2 over 3. The get out of jail free card is the quadratic formula, x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So when you're using the quadratic formula, it's always very important just to write out what the a value is, what the b value is, and what the c value is. It's good to be just explicit about that. And then when you sub that into the formula, work it out, and you'll get x equals 5 or x equals minus 2 over 3. The graphing method is if you had access to a graphing tool, or if you graphed it out on paper, and if you were sufficiently accurate, you would see that it would cross the x-axis at x equals 5 or x equals minus 2 over 3. But I don't think you'll be asked for that level of tediousness in the Leaving Cert. The nature of quadratic roots, it's always good to be able to look at a quadratic equation and identify what the roots will be, okay? So, if, for example, I'll just clear that. So, a quadratic can intersect the x-axis in a number of ways. It can intersect the x-axis like this. It can intersect the x-axis like this, or it can intersect the x-axis, sorry, it's a bit slanty, it mightn't intersect the x-axis at all, okay? And now, the position of the quadratic with respect to the y-axis is not important here. The point is the number of intersections it has with the x-axis. That's the thing I'm trying to get across. And if you recall in the minus b formula, under the square root, so the minus b formula was minus b plus or minus the square root of b squared minus 4ac all over 2a, okay? So it all depends on what the value of b squared minus 4ac actually is, okay? If b squared minus 4ac was greater than 0, then we know that the quadratic has two distinct roots. It hits the x-axis at this point, and it hits the x-axis at this point. If you worked out and this, by the way, is called the discriminant. It tells you something about the quadratic. It's kind of a discriminator, you know, the English term discriminant. if you found that b squared minus 4ac 4ac was equal to 0, then it has one duplicate real root there. But if you found that b squared minus 4ac was actually less than 0, you would have no real roots and you would have a complex root. You'll come across complex numbers later in the course. So if the b squared minus 4ac was less than 0, then you're getting the square root of a negative number, and that's where complex numbers or imaginary numbers come in. Okay, so it's good that you can use this to tell you something about the nature of the roots of a quadratic even before you work them out at all. Okay. So back to the PowerPoint presentation. You can do this, and you can go from the quadratic. We have gone from the quadratic to the roots. You can do this in reverse as well. If I told you that the roots of a quadratic are r1 and r2, then the factors are x minus r1 and x minus r2, and you can multiply that out, and you will find that the original quadratic is x squared minus x times r1 plus r2 plus r1 by r2, okay? And in words, this is x squared minus x times the sum of the root plus the product of the roots. So that is interesting. That is important to know. Given the roots, can you go back to the original quadratic? Okay. So we have done. This is another foray into coordinate geometry. So we've taken linear equations and we have found their intersection. Now we have a curve, potentially a quadratic, and we want to find where it intersects with a linear equation on the Cartesian plane. So we have, for example, here the simultaneous equations, x squared plus xy plus 2y squared equals 4. And we have 2x plus 3y equals minus 1. Now we can plot them, and we want to see where they intersect, okay? So that's the intersection here. If you were to plot that curve, now it's not a quadratic it's not a quadratic as we have encountered so far. Nevertheless, it is a curve, okay? And that is the curve shape here, and this is the line, and it intersects at 2 points, okay? And the x and y coordinates here match both the line and the curve at the same time. The x and y coordinates of this point match the curve and the line at the same time. So you have to work out what they are, okay? So if I can just step through that briefly. So the method of this is a little different, and I won't do it in its entirety because I'm kind of cut for time. The method is a little different. So we have x squared plus 2x, x squared plus xy plus 2y squared equals 4. And we have 2x plus 3y equals minus 1. Okay? I mean, all these results, all this work will be posted up later on YouTube, so you'll be able to revisit it later. Like using the same theory as the previous simultaneous equations, we have to remove a variable. We have to get rid of it, okay? So what we can do is we can express x in terms of y. Okay, so if we take the second expression here, we can say that x equals minus 1 minus 3y all over 2. And then what we do is we sub that value, that expression for x, back into the first formula. So we have minus 1 minus 3y all over 2 by minus 1 minus 3y all over 2 plus minus 1 minus 3y all over 2 by y plus 2y squared equals 4, okay? Here, we're back to pure algebra. So this is the minefield of manipulating indices, watching for your signs, and watching for your, preserving the equation, making sure whatever you do to the right-hand side, you do to the left-hand side. So that is algebraic simplification. But the thing is that when I do all that, I will pop out with what 11y squared plus 4y minus 15 equals 0. I recognize that as a quadratic, okay? I can factorize that to be this, and that's minus 1 and plus 15, because 11y minus 1 plus 15y is plus 4y, and plus 15 minus 1 is minus 15. So therefore y equals minus 15 all over 11, or y equals plus 1. So then, if I sub in this value for y into this expression, I'll get a value for x, and that will be 17 all over 11 into and minus 15 over 11. That's 1 point. And then the other point, when I take this value of y and I sub it into this expression for x, I get minus 2 and plus 1. So again, the method is different, but the philosophy is the same as the simultaneous equations. I am removing one of the variables from my work and to get it all in terms of one variable. So I chose to remove it. I chose to get rid of the x. I could have got rid of the y's as well. All right, maybe you'd like to try that on your own. I'm not sure how easy or difficult that is. But ultimately, I come out with 2 points, and that's what you're expecting. 2 points, okay? So a new section here is polynomial long division, and I alluded to this at the outset of the presentation. Sorry, not the outset of the presentation, but during the early part of the presentation. Polynomial long division, okay? Let's say we wanted to divide x cubed minus 2x squared minus 4 divided by x minus 3, okay? So this is similar to the arithmetic numerical long division. So again, we write it out in pretty much the same way. We can say that x into x cubed is 2x squared. And then what we do is we multiply this x squared by the x minus 3. So we have x cubed minus 3x squared. And then we subtract this from this expression. So that's the x cubed minus x cubed is 0. And minus 2x squared minus 3x squared is plus x squared. And then you bring down your plus 0x. So the reason why I included a plus 0x here was just to lay out my work better. I mean, I've done nothing to the polynomial by adding a plus 0x, but you'll find that it's useful in a moment. And I bring it down vertically down here, okay? So now what I do is I divide the x into x squared, and I get x, and I take this x and I multiply each of the terms here. So x by x is x squared, and x by minus 3 is minus 3x. I subtract, and I have plus 3x, and I bring down the minus 4, okay? And then I divide x into this 3x, and I get 3, multiply the 3 by the 2 terms here, and I get 3x minus 9, and I get a remainder of 5. Now, it's always a little disconcerting when you get well, not always, but we like things to add in, to divide in evenly. Sometimes they don't. In this particular case, they don't, okay? So in English, we could say that when we divided x cubed minus 2x squared minus 4 by x minus 3, it goes x squared plus x plus 3 times with a remainder of 5. So we could, rewrite that as this particular expression here, okay? X cubed minus 2x squared minus 4 is x minus 3 all by x squared plus x plus 3 plus your 5 remainder, okay? So just keep that in mind at the moment, just that expression. We'll come back to that very shortly. We have described how to factorize quadratic equations. They are polynomials where the highest power is 2. Now we want to describe how to factorize cubic equations. This is polynomials where the highest power is 3, okay? And again, what does factorizing mean? Factorizing is what are those things that when multiplied together give you back your original expression. This cubic expression, for example, can be factorized like this. If you went to the trouble of multiplying this out, you would get back this original expression. But how do you find these factors? That's the detail. Factorizing cubic expressions is on the course very much, and it is an application of the factor theorem, okay? And the question is then, well, what is the factor theorem? I just want to show you a bit of a background to the factor theorem. It's not on the course, but it's very interesting. And it's like, when I read the factor theorem, I get the same kick out of it that I do when I look at those mathematical videos on YouTube. There's some really cool things there. And this is a similar mindset. So the background to the factor theorem, recall that when we divided this expression by this expression, we got the x squared plus x plus 3 with a remainder of 5, okay? We did that a moment ago. So we rewrote that as this expression here. So x cubed minus 2x squared minus 4 was x minus 3 all by x squared plus x plus 3 plus 5. So in other words, f of x, we could say, is x plus 3 by x squared plus x plus 3 plus 5, okay? Now this is an equation, okay, in algebra. We can do whatever we want, but we have to do it to both sides. Let's say I said, let x equals 3, okay? So f of 3 is 3 minus 3 by 3 squared plus 3 plus 3 plus 5. Therefore, f of 3, the original polynomial evaluated at 3, is 0 times 3 squared plus 3 plus 5. Okay, or the original polynomial f of 3 is 0 times all this plus 5. F of 3 equals 5. Okay, that's a very interesting result. What we're saying is, so what we said before is that when we divide f of x by x minus 3, the remainder is 5, okay? Or in other words, when we divide f of x by x minus 3, the remainder is f of 3. Isn't that very interesting? So if I tell you, well, what's the remainder when you divide a polynomial f of x by x minus 3? All you have to do is work out f of 3. You don't have to go through the long division, okay? Okay, so just reiterate, when we divide a polynomial f of x by x minus 3, the remainder is f of 3. So the factor theorem, just getting on to the factor theorem, if we just generalize the last statement that we made, when we divide f of x by x minus c, the remainder is f of c. But what happens if f of c equals 0? In other words, there's no remainder at all. Okay, so if f of c is 0, there's no remainder. Well, it means if there's no remainder, then the thing that we divided in, the x minus c, divides in perfectly. Okay, so in other words, x minus c is a factor, okay, of f of x, right? So that's the reason why we can state the factor theorem. So if f of c is 0, okay, then i.e. if c is a root of f of x, in other words, where it crosses the x-axis, then x minus c is a factor of f of x. Or we can state it in reverse. If x minus c is a factor of f of x, then f of c equals 0. In other words, c is a root. Okay? So the remainder theorem in mathematics, remember, it states that when we divide f of x by x minus c, the remainder is f of c. But the factor theorem is a particular example of the remainder theorem. When there is no remainder, then x minus c is a factor. So, to reiterate the factor theorem, if f of c equals 0, then x minus c is a factor of f of x, or stated in reverse, if x minus c is a factor of f of x, then f of c equals 0. In other words, c is a root. Okay, this is important for factorizing cubic polynomials. Okay, and there's a slightly more general case here of the factor theorem. If f of k over a equals 0, in other words, if k over a is a root of f of x, then ax minus k is a factor of f of k. Or in reverse, if ax minus k is a factor of f of x, then f of k over a is 0. K is a root. So what's the purpose of the factor theorem? The purpose of the factor theorem is to factorize cubic polynomials. Okay. One question here given in 2017 was, the function f of x is 2x cubed plus 5x squared minus 4x minus 3. Okay, and x is a real number. Show that x minus 3 is a root of f of x, and find the other two roots. Okay, so how do we show that? How do we show that anything is a root? Okay, so I'll go to my whiteboard and I'll clear that. So recall that f of x is 2x squared plus 5x squared minus 4x minus 3. Show that minus 3 is a root. Okay, well, if minus 3 is a root, then f of minus 3 equals 0. So in other words, we have a graph of a cubic polynomial, something like that maybe. Okay, and this is minus 3 here. So if it is a root, if the graph of the cubic polynomial does indeed cross the x-axis at this point, then f of minus 3 is 0. Okay, the y value is 0 on the x-axis. So we take f of minus 3. So therefore 2 into minus 3 all to be cubed, plus 5 minus 3 all to be squared, minus 4 of minus 3 minus 3. So that is 2 by minus 27 plus 5 by 9 minus 4 by minus 3 minus 2. So that's minus 54 plus 45 plus 12 minus 3, and that equals 0. So because f of minus 3 is 0, therefore minus 3 is a root of f of x. Okay. The question then says, what are the other roots? So just to be clear, and find the other roots. Okay. So we might as well, we've gone to the trouble of proving that -3 is a root. We might as well use that result. So if -3 is a root, if -3 is a root, by the factor theorem, x plus 3 is a factor. Okay? X plus 3 is a factor. So we can divide x plus 3 into the original polynomial and we won't get any remainder. Okay? So we have x plus 3, I'll do it up here, x plus 3 into 2x cubed plus 5x squared minus 4x minus 3. That equals 2x squared. So x into 2x cubed is 2x squared. Okay, then we multiply it out. So 2x squared by x is 2x cubed. 2x squared by plus 3x is plus 6x squared. Okay, so 2x cubed minus 2x cubed is 0. 5x squared minus 6x squared is minus x squared. So bring down your 4x. Okay, x into minus x squared is minus x. And that's, so then minus x by x is minus x squared minus 3x, x squared minus x squared minus x squared, that's minus x squared plus x squared, that's 0, and minus 4x minus 3x, that's minus 4x plus 3x, that equals minus x. Okay, and bring down your minus 3. So therefore x into minus x is minus 1. So minus 1 by x is minus x minus 3. And minus x minus x is 0. Minus 3 minus 3 is 0 as well. So it's 0. So x minus 3 is a factor. And the other factor is the 2x squared minus x minus 1. So can we factorize this anymore? Can we factorize that anymore? We have 2x by, and that's x minus 1 plus 1. Okay, so that's one factor, that's another factor, and that's another factor. So therefore the roots are minus 3, x equals minus a half, and x equals 1. Okay? That makes sense? All right. I'll go back to the PowerPoint presentation. So just to reiterate the rules about factorizing cubic expressions, you have to find one root first, okay? So what you do is, in that example, we were told that minus 3 was a root, but sometimes you mightn't be told any roots at all, okay? And you have to experiment with different roots to find one, and I can show you that in a moment. Once you do have that root, k, well, you know by the factor theorem that x minus k is a factor. So what you do then is you divide, as we did, you divide x minus k into the cubic expression to get a quadratic expression, and you factorize that further. Okay, so that's basically what I did in the last question. Okay, So the question is, if you weren't given that x equals -3 like we were in that question, what would you do? Okay, what starting value of k would you use? Okay, and the trick is that this is a general cubic polynomial here. You check all positive and negative factors of the final constant d here. And the reason is that eventually, and this is the last question we stated, because when your polynomial is this, and when it is finally factorized, you'll have your set of factors will be out like this. And at some point, the +3, the -1, and the +1 will be multiplied, have to be multiplied together to give you back your -3. They have to give you back your constant, okay? So when you choose a root, when you choose your starting root, it's going to be the +1 or the +3, for example. It has to be a factor of that, okay? So we'll just do an example there. Solve the equation, and we'll make this the last one now because time is pushing on. Solve the equation x cubed minus 3x squared minus 9x plus 11 equals 0, okay? And write any irrational solution in the form a plus b square root of c. Now I have two more poll questions, okay? These are the last two. Do you know what the term irrational means? Okay, Jerry mentioned this last week, and I think he had a very good explanation of it. Do you know what the term irrational means? Okay, all right. So, as Jerry said, it didn't mean, something that's not sensible. Irrational, in other words, it cannot be written as a ratio. It cannot be written as a fraction. Okay, so it's the third one there that applies. The second poll question, do you know what the z means in that question? Okay. Yeah, the final one here is correct. No, it's not a complex number. Complex numbers are they're not represented by the letter z. So z is an integer, and an integer is any number, any negative whole number, any positive whole number, or 0. Okay. So just to go back to the question, write any irrational solution in the form a plus b root c. So he's kind of hinting, the question is sort of hinting that you'll probably hit an irrational solution, okay? And he wants them expressed in integers. So again, you have an idea of where this question is going, okay? You have an idea of what sort of answer that is probably expected, okay? So again, time and time again in the course, you will see that, a question is to be expressed in a particular manner, and he will use, R for real, Z for integers, and he will use terms like rational and irrational. And it's those terms that are not repeated, they're not explained enough in the course. I think there should be a little box at the start of every chapter that explains what those types of numbers are, just like the Venn diagram that Jerry had last week. So it's important to have that in your mind all the time. So if we take a look at this question, and I'll share the whiteboard. So we have, sure. We have x cubed rather, minus 3x squared minus 9x plus 11 equals 0. So what's our starting root? Okay, what are we going to do? Well, what we do is we take this 11 and we factorize it. What are the factors of 11? Minus 1, plus 1, minus 11, and plus 11. Okay? What we do then is we see if any of these are roots. So are any of these roots? Okay? So we have f of minus 1. And sorry, what does it mean to be a root? Okay? That's when f of the number k, let's say, equals 0. That's where it crosses the x-axis. Sorry, crosses the x-axis. So if we worked out f of minus 1, okay, so minus 1 all to be cubed minus 3 times minus 1 all to be squared minus 9 by minus 1 plus 11. Does that equal 0? It does not. Okay. What about if we I'll just jazz it up a little bit. I'll deliberately take the long-winded way. But what if we chose f of minus 11? Okay, then we have minus 11 all to be cubed minus 3 times minus 11 all to be squared minus 9 times minus 11 plus 11. That doesn't equal 0 if you were to work that out in the calculator. F of 11, that's 11 all to be cubed minus 3 times 11 all to be squared minus 9 times 11 plus 11. That does not equal 0. So f of plus 1, test that. That's 1 cubed minus 3 times 1 squared minus 9 times 1 plus 11. So that's 1 minus 3 minus 9 plus 11, and that does equal 0. Happy days, okay? Now, if I was in an exam and I knew that I had to try 3 particular values, I mean, I would leave the 11s till last because I don't want to be working out 11 cubed in my calculator unless I can avoid it, okay? So I would work out the f of minus 1 and the f of plus 1 first, just to see would they be roots. However, it could well be that you have to go the whole hog and work out, it could be on the very last value that you choose. It's kind of the luck of the draw, okay? That I deliberately skipped to the minus 11 here, just to show how, you know, you mightn't get the answer straight away, okay? So eventually I said that plus 1 is a root, okay? Therefore, by the factor theorem, factor t, x minus 1 is a factor. Okay, so with that x minus 1 as a factor, we can we can go back to our long division because we want to work out the other roots. And remember, they might be irrational, and we might have to use integers in that expression. So x cubed minus 3x squared minus 9x plus 11, okay? Then we multiply in the x into x cubed. We have x squared. So we multiply the x squared by x is x cubed minus x. So x cubed minus x cubed is 0. And minus 3x squared minus x is minus 3x. Sorry, that should be a square there. Minus 3x squared minus x squared. That is minus 3x squared plus x squared, which gives minus 2x squared. So bring down your minus 9. Okay, x into minus 2x squared is minus 2x. So we have minus 2x squared plus 2x. Minus 2x squared minus 2x squared, that gives you 0. Minus 9x minus 2x is minus 11x. And bring down your 11 again. And then we have x into minus 11x is minus 11. So we have minus 11x plus 11, and that's 0. So we have the other factors are in x squared minus 2x minus 11, okay? Now, can we factorize that? No. Well, we can't factorize it by inspection anyway, because there are no factors of minus 11 that would give kind of a minus 2. So we're looking at the minus b formula. So a equals 1, b equals minus 2, c equals minus 11. Okay, remember I said when introducing the quadratic formula, I said that it's always good to write down what your a value is, what your b value is, and what your c value is, okay? So we say minus b, which is 2 plus or minus the square root of b squared, which is minus 2 all to b squared, minus 4ac all over 2a. So therefore it's 2 plus or minus the square root of 4 plus 44, that equals all over 2. So this could get kind of tight here. If I just, sorry, I made some space over here. So that is 2 plus or minus square root of 48 all over 2, okay? And that is 2 plus or minus, let's say, the square root of 16 by the square root of 3, okay, all over 2. So that's 2 plus or minus 4 by the square root of 3 all over 2. That equals 1 plus or minus 2 by the square root of 3. So they are the other roots. Okay, is that it? There are, just as you can you can predict, recall that we could predict the shape of a quadratic equation by using its discriminant. Now, there is a discriminant for cubic polynomials, but it's not on the course. It's quite complex. But just be aware that a cubic polynomial can exist can have distinct shapes. So if I went back to my whiteboard, so I'll just leave you take that down if you're still taking it down. So, okay, I'll clear that. Cubic polynomials can exist in a number of forms. They can exist in this form, for example. So it has 1, 2, 3 roots. Okay. It can exist in another form. One, and these are 2 repeated roots. So these are 3 distinct roots. 3 roots, 2 of which repeat. And that's the repeated root there. And then finally, then we have one real root and 2 imaginary roots. Okay. That's basically it. And I'm not aware of any way of predicting that. I don't believe there's a discriminant on the course that'll predict it. But it's good to know what the shapes of the underlying cubic polynomials can be. All right. I'll go back to my PowerPoint presentation. So I have a final example here. I won't do it on the whiteboard. I'll just narrate my way through it. But we have a cubic polynomial here. As you can see, it cuts the axis at 3 points. Hence, it has 3 roots: -3, -1, 2. Hence, the factors are x plus 3, x plus 1, and x minus 2. So when you multiply out those factors, you get back this original polynomial, which he asks you to confirm. Okay, that just shows the relationship between the factors and the original polynomial. All right, I think we'll leave it there. It's 12:30. I don't want to keep you any longer. And if you have any questions, please let me know. Thank you for taking part in the poll questions, and I'll hand it back over to Eamon.
Thank you, Paul, for a very clear and interesting presentation. I suppose I just want to put up a screen somewhere. So just to recap some of the resources that Paul mentioned were number file 3 blue and 1 brown, mind your decisions, and there's another one that I remember using, GeoGebra, which is very handy for plotting functions. You can just input your function, it'll draw a graph for you automatically. So I think that's all for this week, and see you next week for the Algebra 2 and complex numbers and Cartesian form tutorial. Okay, so bye for now.